In this video, we're talking about second-order partial derivatives of a multivariable function, or higher-order partial derivatives. And we already know how to take first-order partial derivatives of a function. So in this particular problem, we've been given the function f of xy is equal to x squared plus e to the y squared. And we know that if we wanted to take first-order partial derivatives of this function, we would take the partial derivative of f, that's what this notation means, partial derivative of f with respect to x, and because there's this other variable y, we would also take the partial derivative of the function f with respect to the variable y. But when we take second-order partial derivatives, we have to start by taking these first-order partial derivatives, and then, in a sense, take the derivative again of these first-order derivatives to get the second-order derivatives. So let's start by taking the first-order derivatives. Remember, if we're taking the partial derivative with respect to x, then we treat x as the variable, and all other variables we treat as constants. So in this case, y we would treat as a constant. So like this e to the y squared term, if we imagine y as a constant, let's pretend, for example, the constant is 3, then we'd have 3 squared here, which would be 9. We'd have e to the 9, and e to the 9 would also be a constant. The derivative of a constant would be 0. So when we take the partial derivative with respect to x, this whole term here, because it doesn't involve a variable, it doesn't involve the variable x, then the derivative of this whole term will become 0. So the derivative of x squared is simply 2x. The derivative of this term, because there's no x variable, is 0. So the partial derivative of f with respect to x is 2x. If we take the partial derivative of the function f with respect to the variable y, we treat y as the variable and we hold x as a constant. So the derivative of x squared would be 0 because there's no y variable involved. But the derivative of e to the y squared would be e to the y squared, because remember, the derivative of e to a variable is still that exact same thing, e to that variable. But then we have to multiply by the derivative of this exponent. So the derivative of y squared is 2y, so we have to multiply this by 2y. And that's according to chain rule, remember. So then when we simplify this, what we get is 2y e to the y squared. Now these are our first order partial derivatives. If we want to find the second order partial derivatives, there are 3 of them. There's the second order partial derivative with respect to x, and it looks like this. It would be the partial derivative, and then we square that, of f with respect to x, and we square the x variable. This means we start with the first order partial derivative with respect to x, and we take the derivative with respect to x again. So we would take the derivative of 2x with respect to x again, and of course that would be 2. We can do the same thing with y. So we already took the partial derivative with respect to y. If we take the partial derivative with respect to y again, we get partial squared f over partial y squared. And so we take 2y e to the y squared, and we take the derivative with respect to y again. So in order to do that, we need to use product rule. So we can think about the fact that we have 2 functions here. We have 2y multiplied by e to the y squared. So if we want to take the derivative, we have to use product rule. So first we'll take the derivative of 2y, and that's 2. But then we leave the other function as is. So we say e to the y squared. Then we add to that the opposite situation. This time we leave 2y as is, but we take the derivative of e to the y squared. Well, the derivative of e to the y squared is just e to the y squared multiplied by 2y. We already did that when we took our first order partial derivative. So now we simplify here, and we just end up with 2e to the y squared plus 4y squared e to the y squared. If we wanted to here, we could factor out a 2e to the y squared, and we'd end up with 2e to the y squared times quantity, 1 plus 2y squared. Now the third second order partial derivative is what we call the mixed partial derivative, and its notation looks like this. We say partial squared f of partial x partial y. And we can get this in one of 2 ways. We can either start with the first order partial derivative of f with respect to x and take the partial derivative of this with respect to y. Or we can start with the first order partial derivative of f with respect to y and take the derivative of this with respect to x. So it's like we're going the opposite way. Here we started with x and we took x again. Here we started with y and we took y again. That got us our first 2 second order partial derivatives. But to get the mixed second order partial derivative, we either start with x, then differentiate with respect to y, or start with y, then differentiate with respect to x. The cool thing is that you're always going to get the same answer no matter which order you do it in. So if you start with x and then do y, or you start with y and then do x, you should get the exact same answer. If you don't, you did something wrong. So that can often be a good way to double check your first order partial derivatives. So let's do it both ways. Let's say we start with the first order partial derivative with respect to x, there's 2x here, and we take the derivative with respect to y. Well, in that case, there's no y variable involved, so the derivative would just be 0. If, on the other hand, we started with the first order partial derivative with respect to y, so this 2y e to the y squared, and we then took the derivative with respect to x, there's no x variable involved here. This whole thing is a constant because we're treating y as a constant. So the derivative would again just be 0. So you can see that no matter which way we go, we end up with a mixed second order partial derivative of 0. And these are the three second order partial derivatives of a multivariable function.